Okay, so this is, we've talked about average rate of change, slope. Didn't need this class, already knew that. And then we moved to the instantaneous rate of change where we wanted it exactly one value. And we said the instantaneous rate of change is a derivative. And that's all we've said. And then we came back and we said, well, if the derivative is a slope, a number, then we could say what's going on, the instantaneous rate of change, at a certain point. And then we said, well, what if I want 3, you want 2, you want 7? I don't want to keep doing that. So what we did last class is we said, instead of a number, a slope, let's come up with a function so I could plug in an x value and then I could get the slope. And that's kind of what we did last class. And if you missed last class and not staring at anybody, don't forget, and yeah, I meant to say that in the email, don't forget, go listen to the lecture. And if you listen to the lecture, if you miss a class and you're just like, I don't know what's going on, then definitely come see me, okay? Come talk to me. All right, so now we've said a derivative is a slope, it's an instantaneous rate of change, but we kind of want it applied. Now, unfortunately, we have all this crazy notation. Being a math major, you have to take things like history of math, which is actually kind of cool because you get to hear the funny stories that, I'm going to show you probably 7, 8 different ways how to write a derivative. Why? Because these people in the old days couldn't get along. One would say, well, I want to use my notation, and another one would say, I want to use my notation. And it's kind of like engineering students versus biology students. You guys write things different ways, so it's the same thing. So we're going to talk about different notation. This Leibniz notation I probably like the best, and as I told my morning calculus class, the reason why is it's what I was taught. Okay, and so, but there's actually a better reason why I like it. Then we're going to also look at determining the units of a derivative, which is why I like this notation. And then we're going to actually interpret the derivative using these units. And then the whole shebang here is to be able to predict future values. Now, when we get to this part right here, some of you guys are very logical and good thinkers, and then some of you aren't, right? That's funny. But I've noticed when I've given this information, many of my students go, man, you ain't got to do all that. You got another way of doing it? I don't care. I'm not one of those teachers. You got to do it my way, okay? And I think you'll see when we get to this. But what happens here is we say, well, maybe I want to predict, I know what's going on right here, or maybe I want to know what's going on right here. And that's all we're going to use. All right, so if we have a function, okay, so y equals f of x. These are just different ways that you will see derivatives written. Y prime, f prime x, and f prime. Again, it depends on my mood, what I'm doing. I probably will use this one a lot. Okay, and again, it's just how I was taught. And I kind of like it better because it makes sense, because it looks like the function. It just has the little prime thing. That's the one that I really like. And so Leibniz said, well, that doesn't make any sense to me. And he said, I'm going to write this derivative as this dy dx, or the derivative of the function over dx, or this d dxy. Well, the reason this makes more sense to me, I've told you over and over and over, what are you finding in here? Slope, slope, slope. What's the slope? Change in y over the change in x. Doesn't that look like the change in y over the change in x, delta y over delta x? And so I like this because it makes sense. That's one reason. The second reason, it helps you. You can think of this like a fraction. It's not a fraction, but you can think of it like a fraction and get your units. When you get through and you work the problem and you say, the answer's 3, and I go, 3 what? And you're like, I don't know, I just got 3. You could look at your units, your y units and your x units, and write them as a fraction, miles per hour, something like that. And that's why this is by far my favorite one. You're going to see, it's unfortunate that the dude that wrote this book, he uses all of these. So one time he'll ask you to find that, and you'll be, I don't like this at all. I just feel like something's missing. This, of course, is saying find the change in my function over the change in x. Well, isn't my function my y? And this is just simply finding the change in my y, just threw it out over here where my x is changing. Okay, so just different ways to say always ask me, you know, if you're like, are you asking me to find the derivative, or are you asking me to find a value of a function? So if I have the cost C of steak in dollars is a function of the weight W of the steak in, I could write this change, in other words, the change in the cost over the change in dollars, which would make sense. You're going to have the cost is going to go up if you have, you know, more pounds of a steak. If I have the number N of gallons of gas left in a gas tank is a function of the distance, D, in miles the, well, I can simply write this as a derivative, how it's changing, the gas is leaving the car. In other words, as the number of gallons is going to go down in this case. So, I mean, you could even say that this would be, if I'm getting larger steaks, would be a positive derivative, and this would be a negative derivative as I continue. Okay, so if I have a function here, and I throw this ball up in the air, and this little red thing, awesome, I just sit there and play with that all day long. I'm trying to hypnotize you. Now cluck like a chicken. All right. So if this is a function, okay, S equals f of t, let this be the height of the ball at a particular time. What's the height right here? What's the height right here? And so on. Okay, so that's all we have is we just... The derivative, so you see I've written this as f prime of t. So the derivative is the velocity, and you're going to hear that over and over again. The first derivative is velocity. We do other derivatives; they mean other things.
So is the second derivative the acceleration of the ball?
Yes, and we will get there. And so the first derivative, all you need to know right now is the velocity, the speed at a particular time. Okay. I don't like a lot of times you will see this v equals because I don't know what v is, and if you don't know that it's velocity, you don't know if this is the original function. We write it as a derivative. Again, I kind of like this because this is going to tell me my s here is the height of the ball in feet, and my t is time in seconds, so I know if I want to find the velocity, I know it's going to be feet per second. And that's why I like this. It helps with my units. And sometimes students have a hard time with the units. When you read through it, and you'll see, you'll have some exercises where you don't even work a problem. You just say, what's the units in this? Okay, to try to figure it out. All right, and so our dependent variable, what depends on, okay, our feet depends on what second we're talking about. Our dependent variable always goes on the top, which is a good thing to know as well when you actually are trying to set the... All right, if I want to interpret this, the height of the ball is 8.84 feet at 0.1 seconds. And let me preface this with, I'm just giving you information. We haven't calculated anything. I'm just telling you the height of the ball is 8.84 at times. So what this means is if I evaluated this function, I don't have a function, but if I had one and I evaluated it, so you're used to seeing this in algebra, f of 3, and you plug in the 3. This is saying that the height of the ball, okay, s of 0.1 equals that. The derivative, the velocity, is 16.8 feet per second. And I throw this in here because I had students always ask, where'd that number come from? I just give it to you, okay? This is given information. So we know the height of the ball at a particular time, and we know how fast the ball is moving. Okay, so the velocity at that particular time, to write that kind of all mathy looking is notice that here I'm talking about the derivative, where here I'm talking about, and do you notice the difference? He's Justin, baby, you know, he's got some... You don't hear about him much anymore. All right, this was way funnier last semester because he was all in the news. All right, so the big difference, though, is just that little prime thing, meaning by looking at it, that's the difference. But this is a huge difference because this is the height of the ball, and this is how fast the ball's moving. Okay, that's the big difference. The value of the function, in this case, is the height. Hello. And the derivative is the speed of the ball. This is how,
Wait, I thought speed is always...
Velocity, speed.
Wait, I thought speed is always... Oh, never mind.
Absolute value of velocity.
But, so, we can say speed as velocity? Or?
If you say absolute value, yes. Yep, because it's always positive. This is how, again, I'm used to seeing it. And when we get to evaluating derivatives, you'll probably see me write it more this way. This says that I have my derivative, and this bar says evaluate my derivative at that value. Now, this is kind of wishy-washy showing you this stuff, because if it was me, I'd be saying, what derivative? I haven't given you a function. There's no function here, okay? We're going to get to that in a minute. But if you had a function, you'd take 0.1 and you'd plug it into it, and that's the value that you would get. All right, so, and again, I'm just trying to give you lots of different ways you'll see this written. Here's where I mentioned that I don't like this. Because unless you know that V, I mean, that V could stand for vultures, right? I mean, who knows what the victory, right? Unless I tell you that's velocity, you don't know that that's a derivative. So I tend to not like this, and that's what they're saying. This is velocity at this exact time, and that's how fast the ball's moving. So just different notation. And again, if you're not sure, just, you know, especially on a quiz, is that the value of the function, or is that the value of the derivative? All right, so here I have, once again, my derivative is 16.8. If I use that Leibniz notation, I would know that's in feet per second. So at time 0.1 seconds, the ball is traveling at a rate of 16, wow. And that's everything that'll be on the final exam. All right. Okay, so at time 0.1 seconds, the ball is traveling at this rate. So the rate of 16.8. I think when I hit mix, it does it right here. So, and kind of like you're saying, and you're going to see this is going to show me doing this, kind of what you're saying, this stuff was given.
Okay.
Yeah, and so that's how I got the 1.68. Yeah, that stuff was given. Oh, well, no, I want to show him here. Say, especially if you're throwing the ball up in the air, somebody getting beat. and it hits a height, and then it comes back down. You should be thinking it's not going to be going the same speed, right? I mean, it's going to go up a certain speed. It's going to start to slow down, then come back down and go fast. Well, but remember what we're saying. We're saying at exactly that time. We've measured it really, really close to that time. So kind of go with the speed's constant. It's not, but kind of go with it because we're looking at this time. So the ball will travel approximately 1.68 feet during the next 0 point. I think that's where I was. So if this messes up, to German boy. All right. I think it's going to be fine. It's happened in another class. So I add the change. Okay, so it changed, and I get my final value. So what this value was at time 0.1, the value of the function. This taking, as Chris asked this value, I'm taking how much it changed. Yes, I'm sorry, I didn't see you.
So for this problem, are we supposed to ignore the acceleration of gravity?
That's what I was saying. Let's pretend we're in a and it's not that we're in a perfect world. It's more that I'm at exactly that point. We're talking instantaneous rate of change right now. So I have zoomed in at 0.1 second. So if I'm exactly at that time, then it's not going to be changing. Okay? But yes, we're ignoring real life, right? Yeah. Huh? Yeah, it's real life. Who needs it, right? All right, so again, our formula, and I don't know why this loses some of these characters. I don't think they do on your slides, because your slides are PowerPoints, these are PDFs. So the format here is and which would make sense. The original value plus the change. That's all it is. That's how much we're going to get our new value. So we take our original value of our function. Our change here is how fast it's changing, and then what is our interval here. And this, of course, this interval, and this is what I'm saying, we're making this interval very, very small. What I want to know is from 0.1 to 0.2, I want to know now what the height of the ball is. Okay, so I've kind of zoomed in to get, and I'm saying that this change, this movement here is going to be constant. It's going to be the same.
Isn't that the point slope point? Can you just use point slope?
And all I've done here, now my minus signs come back, So I don't know why students don't like something on the right side. So all I did is brought this around, because what I'm doing, this, as Chris was asking, so what was given? This information was given. This information was given. This is what wasn't really given, because I said I want to know at 0.2. Now what I'm doing is I'm taking this information, how it changed, find me a new height, and now I'm going to go see, well, now what's the height at 0.2 seconds? Well, I mean, as you mentioned, we're ignoring gravity. So if I keep doing this, in your head should be, this is a pretty bad approximation, right? If we want to approximate in, say, 3 seconds away. I'm doing this in 1/10 of a second, so it's not a great approximation. And that should make you happy right there, approximately. And so this is what the formula actually looks like, where we say at a particular time, I want to know the height. And the S was my height, remember, of the function of this ball. So whatever you're doing, your actual function, how do I find it? I look at a particular time, okay, that I'm interested in. I see how it's changing, and this is my time interval. From like up here, 0.2, or 0.1 to 0.2, how big is that interval? Okay, and that's all that piece is. So this is how you're going to see. And again, why the approximation is we are assuming that this rate of change is constant. And again, it's because of that right there. It's not that we're really saying, man, we are really pulling a fast one because this is not constant. We're saying, but yeah, it is if I have zoomed in far enough, because what I'm saying is I have this going on, and I'm telling you I'm only looking at exactly right there. Exactly right there. And that's why the speed is staying constant. And if I go just a little bit over to 0.1, there's not going to be that much change. Is there going to be change? Well, yeah, but not that much. And so as I just mentioned, well, if I approximate over here, it's probably going to be a pretty bad approximation. And what you do in real life is you try to get another data point. You say, well, I know this was given to me. I can approximate something close by it. What is a derivative? Where you're looking at something very, 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 very close. But then if I want to approximate something up here, I probably better try to find some data points around it. And then, of course, I'm going to get a better approximation. So in doing this, we are using the tangent line right there. I stuck the tangent line to the function in place of the function. We're actually looking at the tangent line now. We could erase this parabola. We're not even looking at the actual. All right, so how the tangent line, how this is actually formed. Justin, what did you just say? That's what he recognized. That's all you're doing. And sometimes it's difficult to recognize it because it's kind of moved around. But what we're doing, if I'm doing a tangent line, and you guys had to find the equation of the tangent line at a particular point, that's what we're doing. We're just moving our point over a little bit to make our approximation. So this is our point slope form. It just flipped. I know these kind of look weird when they flip. I'm going to call my point A. So my y value would be my function evaluated at A. That my x1, y1 is A, comma, f of A. So all I've done, I'm calling it different things. Why am I calling it different things? Because I'm going to substitute this stuff into my point slope form of a line equation. Okay, so this is my point of interest. The value of my function at my point of interest. I'm going to rename these so I'm into this function. And so since the tangent line is the slope of the line at the value of the function, you got to get that. The tangent line you get the slope out of it, of the value of the function, then I know what m is. It's just f prime of A. It's the derivative of the function. And so together, I start right here with my first line, my point slope, and I just start plugging things in. Well, the first thing I do is take this minus y and throw it to the other side because I want it to kind of look like what I've been showing you. Well, y1 up here, we said let that be f of A. My slope is my f prime of A, and then I have my x minus my x1, which is my A, and this is exactly what I just showed you. So that's what you're doing. You're taking the point slope form of a line and you're kind of manipulating it. and saying, well, I want to know what's happening here, and then I kind of want to move over whatever that distance is right there to make some sort of. But again, you know, I mean, and this is good you guys are asking this question about, you know, real life. This is definitely approximation, okay? It's a good approximation if you need something close by, and that's the big key if you're looking for something. And so in other words, we're basically dealing with math magic here, is because we're saying that this is approximate. Then what we did is we used this equation to use it as a prediction, to predict something later. And I mean, this would be like you doing, you know, your work. Now I know, you know, it reminds me of seeing you guys doing one of the last group works, and it said find the instantaneous rate of change. And I'm walking around and everybody's writing that f of x plus h minus f of x over h, and which is good because you knew that's what you use for instantaneous rate of change. And I'm like, but where's your function? You had a table, remember? And I think that confuses you guys sometimes when you see two different things here. So, you know, well, when would I ever use this? Well, if I want to predict something in the future, you know, I want to predict something fairly close. I either know these values, because remember, you never saw a function. I just give you values. I either know these values or I have a function. As you can imagine, that's what we'll get to later. We will actually find the derivative of the function and make these approximations. All right, use the tangent line approximation to predict the height of the ball at time 0.5 seconds, given the height and its rate of change 0.4. So all this data is given to you, okay? What we want to do is we want to predict this. We want to see how good this is. In other words, I went out and I measured. I threw a ball up, and at 0.1, I found the height. 0.2, found the height. 0.3, and so, well, I didn't do it, but so I have all these values. I'm going to use this value to predict at 0.5. And you might say, why? It's right there. Just because we want to do it as an exercise to see how well this predicts. So if we do it right, we should get 13. And so these values were in that table at 0.4. The height of the ball at 0.4 seconds is 12.44 feet. Given, once again. Okay, this information was given to you in the table. The rate of change of height of the ball, which was also given, that was that far column, is 7.2, okay, feet per second. So this was all, so far everything is being. And so I want to find the height of the ball. Again, it apparently doesn't like equal signs and it doesn't like minus signs. These will be in your slides. I want to find the height of the ball at 0.5 seconds. Well, how do I find it? Tangent line approximation. That's what I'm looking for. This is the information that I know. I know what the height is at 0.4 seconds. I know how fast it's going at that time given to me. I can't really say this was given to you, but you're just saying, well, how far is it from 0.4 to 0.5? I write this out to show you that that's what I'm doing, the x minus a, but most students just put 0.1 right there and go on. So now I plug all this stuff in, meaning that, get these in here so you can see them once again, meaning that I am just simply taking these values that were given to me, okay, the height, 12.44, the 7.2 feet per second, and then I did the 0.1, I'm going to multiply, and I get 13.16 feet, mighty close, and you say, is that good enough? Well, again, it depends on what you're doing, you know. Is 13.16 close enough if you're measuring something by miles, you know? I mean, and you're only, and say you're off by 0.16 of an inch, you know, or something, then that might be fine. But as you can see, and hint, hint, wink, wink for maybe test questions, you could continue to go down here, meaning don't use the 13, use what I actually got, the 13.16, predict 0.6, predict 0.7, predict 0.8. What do you think is going to happen when you get further down? Yeah, exactly. Your approximation is going to be way off. And it's a good exercise to, you know, well, one, it's a good exercise to go through these, but you're definitely going to see that you're going to end up with less precision. So what do? You go back and you measure the ball again. That's what you end up doing. And that's while why a lot of times if you need to do a prediction, you have to keep doing more and more experiments. They say, okay, we know what's going on at this time, but we want to know what's going to happen tomorrow. Well, why don't you come in the morning and rerun the experiment and then do a prediction? I want to know, like at 3 o'clock. All right, different example, okay, so something completely different. When you breathe, a muscle, your diaphragm, reduces the pressure around your lungs and they expand to fill with air. All right, so we got these lung doctors that define the compliance of the lung as the derivative of the function. Okay, so I'm given some data here. It says pressure reduction, centimeters of water, volume in liters. So if the compliance is the derivative, what's the units? Look over here.
Centimeters of water over liters.
I hear centimeters of water over liters.
Wait, no. Liters over centimeters of water. Liters.
Per. There you go. And a lot of that is you finally get after a while, and this is a good example of this, is don't always think that that's your X and that's your Y. I mean, I'll do that just to mess with you on a test, but they do this in the book as well. Don't always think that this is my Y value. I mean, it just so happened in this case. Another good thing that you could do if you're not sure, think of how would you graph this, okay? And then once you figure out your X and your Y, you can figure out what depends on, don't the liters depend on this pressure? And so that kind of helps you. That's, again, why I like the whole say independent variable. Estimate the maximum compliance of the lung. What you do is you look in here, so the increase of volume for a 5 centimeter reduction is the largest. I'm looking over here in this column, and I see the largest is happening right around here. This is a good example. Okay, so estimate the maximum compliance. That's all I asked you. I did not tell you which values to pick. Well, I probably would pick, once again, this largest reduction of pressure, and then all you're doing is actually finding the slope. Okay, that's all you're doing with this. So, in other words, you're finding the derivative, and this is what you guys are doing on your tables, is where you're taking these points, figuring out which one's your Y, your change in Y over your change in. Explain why the compliance gets small when the lung is nearly full. I mean, if the lung is nearly full, it can't expand much more, right? I mean, so in other words, that's why it's slowing down, is when it's nearly full, there's nothing more to expand, okay? So this is what we're going to end up